Alrighty guys, this little black box that you see here with the little yellow circles floating in it is a program I wrote called Taco Space because I'm not very creative. However, this is an example of how you can solve the NBody problem and then animate the solution very easily using Python. Give me just a second, I'll close this out. And so this is going to be a quasi tutorial. It's going to run a little bit differently than other Python tutorials you might see. I am not going to start from the beginning and make you watch me do the whole thing. Instead, we're going to start from the finished program and work our way back to show you how it all works. Right, so this is the finished product that we're looking at here. It obeys the laws of physics, to a reasonable extent. Whenever I learned Python very recently, this is the first thing that I did was figured out how to solve the NBody problem. So real quick, let's go over what that even means. The NBody problem is a physics concept, and we'll go over here to my chalkboard with Steve on it. So the NBody problem is all about gravity, right? So gravity is a force that exists between all objects in the universe and space and time, right? All objects, no matter how far apart they are, no matter what they're made of, if they have mass, they are always pulling on each other. And this is the force here, that's the force of gravity, F of g, is given with the Newton's gravitational equation. We're not doing relativity here, we're just doing classical mechanics. So F of g equals big G, gravitational constant, times mass 1 times mass 2 over the distance between the two objects squared. And that describes the force between the two objects. Right? So the NBody problem says that if you have a universe with directions, right, so an x and y axis, and then if you want to get fancy, you can make it three-dimensional by having a z-axis, right? But so assuming you have a universe with things in it that are all pointing at each other at all times and always accelerating at each other at all times, how do we chart and predict their motions and velocities? Now, in classical physics, this is just a matter of raw computational power, and it's already been solved. There's a couple ways we can do it. This program that I showed you uses what's called a Euler approximation. Euler, a name that may scare some of you. You're allowed to say Euler, I don't care. Euler approximation, what that says is that every object has an x and a y position, and that time is a change in x and y. Right, and so it's gonna run a calculation to determine how much each body should change its x and y position, and then it's gonna do it, and then it's gonna run that calculation again, and that's gonna be time, as it were. Okay, and so in order to do that, we need to know a little bit of math, but we're gonna go ahead and look at the program here. Alright, so this is the program. It is actually not very long. As you can see, it is technically less than 100 lines long. And we can annotate this as we go along. We'll go ahead and short it. It's 94 lines long. Congratulations, everybody. So the way it works is we start off, this is a tkinter module, so we have to import tkinter. We have to import numpy. We import random just as a thing that we can do, but it's not required. The import math so that you can get square roots. And that's all that you need it for. There's actually, the math here isn't too complicated. Right, so we've got our root and our root title, which is taco space. And then you have a tkinter canvas here, which is just a widget that allows you to draw objects on an X and Y plane. And the thing with the tkinter canvas is that normally when you think of an X and Y plane, you think of the two being perpendicular and the origin being centered at 0, 0. That's just a coordinate system. Tkinter canvas uses a different coordinate system where you start at 0, 0 in the top left corner of the window, right? And then this direction is X plus, and this direction is Y plus. So this would be, so if you wanted to go to like X100, Y100, it'd be like right there. And that's the only thing you really need to know about the geometry here. We'll get everything around that. I'm sorry, I just made Steve an albino. You may remember Steve from my last video, but he's not a programmer, so he's here as my totem of human compassion. So in the program itself, after we've drawn the canvas, we're going to define how physics here works. And so we defined G as the gravitational constant from that equation I did a minute ago, right? So F of little g equals big G m1 m2 over r squared, right? So big G is the gravitational constant, and in real life, big G equals 6.67 e to the negative 11, which, if you don't know, that is 0.00000006.67, right? 67, right? So that number, and that's measured in, if you're a science nerd, it's measured in meters cubed. Man, my handwriting is terrible. Meters cubed, kilograms, seconds squared. Right? Whenever you scale it to that particular parameters, you get the G value that we normally use. In this simulation, you can see here that G is several thousand times higher than that, at 0.01. We can actually do some math if we wanted to, but yeah, it's 10 with 9 zeros behind it, more powerful, times more powerful. But that's because we give all of our masses in very low numbers and all of our distances in very low numbers compared to real life. So we're going to define a class called a body, because in physics we typically refer to objects in space as bodies, and bodies all have a set of parameters. They all have a sort of a set of properties associated with them, right? And so bodies all have a mass, they all have a position measured in x and y coordinates, and they all have a velocity, right, which is the change in x and y over each tick of time, right? And so these are the parameters associated with a body in space, and what gravity does is gravity changes the velocity. Gravity causes acceleration in a particular direction, right? So we're going to program, or we already have, a class here called body that has mass, it has an x coordinate and a y coordinate, it has a NumPy array with both of those put together. This is just so that you can give it an initial location, and then the NumPy array is how it tracks its current location over time. If you don't know much about NumPy arrays, it really just allows us to do vector and matrice multiplication and math, linear algebra type stuff in Python. And you always want to set the D type to float whenever you're doing math, otherwise it doesn't know what it's doing. See here that we also have a velocity, which is another NumPy array, and this is a function from another program I wrote that has a little bit more functionality than what I'm doing now, where it actually could keep track in a list of its x and y coordinates over time, and then you could make a graph of its position. And then it also has a radius, and in three-dimensional space, or in two-dimensional space, circles have a volume that is pi r squared, right? And if you were going to have a two-dimensional density, you would have the mass divided by the density divided by pi, and then you take all of that and get the square root of that, and that gets you the radius. Here what we're doing is we want to get the sizes a little bit more compressed, and so we're actually making it so that they are spheres. We're taking it to the cube root, or taking it, you can't do cube roots in Python to my understanding, so we are taking it to the exponent 1/3, and we'll do a quick math aside here, right? So the volume of a sphere equals pi r cubed, okay? If we know the mass and we know the density of an object, we already know the volume. So we'll go with the mass over the density equals pi r cubed. And then so whenever we do some more math to it, we eventually arrive at r, the distance, equals the cube root of the mass divided by the density. And if my math is wrong, and I hope to God that it isn't, somebody please correct me. And what we've done in this simulation is we've given everything an implied density of 1 because we're just dividing the mass. Oh, right, and we also have to take this and divide it by pi. Right, but we've already given everything an implied density of 1 kilograms per meter cubed, but you remember that this thing operates in 2D, but we've given it spatial coordinates that make it, or a volume that makes it spherical. That's all right. We've done something else that really kind of makes it not perfectly scientific anyway. Because in science, gravity in a real two-dimensional universe wouldn't work the way it works here, and I'll get to that here in a second. So we've got a body that has all of these properties, and then every body also has a function called f of g with a parameter of itself and another thing, right? And if itself is the other thing, then it's dv, delta v, its change in velocity, is going to be an array of 0, 0. So what we've done here is it's measuring gravity, and the first thing it does is it checks if it's measuring against itself. If it is measuring against itself, it's not going to change anything. All right, that's very important. Otherwise, you can get overflow errors. So now we're going to continue into the actual physics. All right, and so we need to do a quick aside here. F of g in a vector space, f of g as a vector equals negative big G, because it's pulling. Man, I do not have a lot of room here. We'll make my pen a little bit smaller. Alright, so we've got negative big G times m1 times m2 over the distance between the two objects squared. That's easy, right? But then we've got to turn it into a vector, which means that we need to take object A's position, we'll call that position 1, and we have to subtract object B's position, position 2 from it, right? And then we have to take that and we have to divide that by the distance between the two objects. That'll turn our force into a vector because we've multiplied it all. If you know linear algebra, the point here is that we've turned this into a scalar and we've turned this into a unit vector. Alright, so now we know the force of gravity, and we converted the force of gravity into x and y components. So the force of gravity is now going to be measured in gx and gy, right? And in the program, we have called that dv because it's changing our velocity. Dv equals gx and gy. So what's going to happen is if it turns out that dv, Steve's just going to stay pale for a while. It turns out that dv it winds up being a vector that looks like this. Well, and v started out being like this. Then their sum is going to be this. And this is the new velocity here. So that's all this program does. So we see here that we have to determine the distance between the two objects, which we do by giving it the first coordinate of its position array, which is index 0, which remember is the x coordinate. We subtract it from the other one's x coordinate. We square that, right? Because to get the distance, we're really finding the hypotenuse of a triangle, right? Because if this is here and this is here, and we know that we have a force and we need to turn that force into a vector, we need to turn that into its components here, right, to turn it into that. So we're finding the hypotenuse. All this does is find the hypotenuse between, this self.dist finds the object's distance from the object it's being measured against in the function, right? And if the distance is 0, then we're making the total change in delta V 0 as well. That prevents us from dividing by 0. In this function, if you divide by 0, you will break your program and potentially your computer. It is just not good to do. So now we've got our f function here, that's our force. We're taking negative g times body 1's mass, self.mass, times other.mass. We're dividing it by this distance that we got up here, dividing that by that squared. And then we're normalizing the vector here. And this is the last quick aside I will do before we finish. The reason why this isn't accurate to a two-dimensional universe is that in a two-dimensional universe, it would be big G. It would be big G times mass 1 times mass 2 over just the distance. Whereas in a three-dimensional universe, we make it the distance squared. Right? So this is inverse proportionality versus the inverse square law. So in a real two-dimensional universe, gravity would be much, much, much stronger because it's being divided by the distance instead of the distance times the distance. And so for that reason, we're not actually looking at two-dimensional gravity. We are really looking at a series of frictionless spherical marbles behaving three-dimensionally on top of a frictionless two-dimensional plane. And that's why we gave it that radius cubed value, because what's really happening is that we are looking eye in the sky top down, and that you have these little spheres on a frictionless surface behaving gravitationally. That's how this is really going to be. So truthfully, this is a simulation or emulation of gravity provided in two dimensions. So we have our function for gravity. That's how it works. We take our force here to turn it into delta V. We divide the force by the mass. That turns it into an acceleration rather than just a force, so that it's scaled against the object's mass. Now objects have inertia with respect to gravity. And then what this is doing right here is if the two objects' radii overlap, they're actually just going to reverse gravity, and it'll make it kind of like a squishy collision, and then we'll have a friction coefficient here of 0.5. So when two objects collide in this, it won't be actual hard-coded collisions, but whenever they hit each other, they will still bounce off each other in the end, but in like the kind of like almost phase into each other slightly. It'll be like they bounced off each other's atmospheres or something ridiculous like that. These objects are only a meter wide and measured in hundreds of kilograms with gravity that is billions of times stronger than our gravity, so clearly it doesn't need to be too accurate. And what this is doing right here, all this is doing is it's giving everything borders. Oh, the last part. Once we've turned our force into a vector, we then take that vector and add it to our velocity. All right, and then so our velocity now becomes our total velocity with respect to everybody that we have run f of g against. And what this is doing is it's saying that as part of its gravitational function, as part of physics, if this crosses the borders of the window, things will just bounce off of the borders. And so we have a list here that I made called bodies. This is how we are going to keep track of everything moving in space. We have capital bodies with a number. And then we have our one custom body I put here. I'm actually going to remove this because it's pointless. So now this for loop, for I in range 0 to bodies, right? So now it's for I in range 0 to whatever this number equals. So in this case 25. It's going to add to our list a body with all these random parameters that I gave it. So for every number in here, it's going to create an object and put it in this list. And that object is going to have a random mass, a random x coordinate, a random y coordinate, and a random velocity. And then after it runs that for loop, it's going to start the universe. This is going to be its equivalent of the Big Bang. We're going to say that t, which is our timer, equals 0. This is a safety feature. We're going to say that tx equals true, also a safety feature. This is the loop. Okay, so while tx equals true, is definitely very equal to true, okay, we're going to start a loop. Every time the loop starts, it's going to check and make sure that this value equals true. And we're going to, every time it starts the loop, we're going to add 1 to this value here. Okay, we're going to take our canvas and we're going to delete everything on it. This is going to be the start of our frame. Now, for body 1 in bodies, this is going to be a little for loop that's going to list through every object that is in this list that we just created all of these things for. It's going to loop through our list, and for every object in our list, it's going to run, for every object in our list, that object is going to run f of g against every other object in that list. And then that body's position is going to be added to, that body's velocity is going to be added to its position. And this is again just if it bounces, if it causes a bounce. We won't worry about that. All right, so it's going to update that body's position according to the forces of every other body in the list. And then after it's done that for everything, every single body is going to get an oval drawn on the canvas for it with a x-coordinate modified by the body's radius, right? So it's going to start at an x and y and then draw the oval out by a factor of that object's radius. It's going to draw that object and then it's going to update the canvas and show us what is on the canvas. So it's going to create a frame. And then that's the end of the loop. And then it's going to start the loop over again and delete everything, run everything, all the forces through, update everybody's position, and then draw everybody again and update it. And it's going to keep doing this forever. It's going to keep doing this forever until our safety feature t, which is increasing by 1 every loop, until that equals 100,000, and then tx equals false, and it'll automatically turn off the loop. And all that does is it prevents you from running the canvas forever. It prevents you from, if you put 2,500 bodies by accident and you can't close your computer, you know that if you decide you don't want to unplug it for every reason, it will eventually, at some point, whenever it runs through the cycle, it'll end. And so the end result of this program that has 92 lines in it is a full animated NBody solution that also includes approximated collisions, and things move through space. Every time t ticks up, that is a second. These objects all have random masses and random starting velocities and random starting positions, and then they will just behave according to Newton's laws and the parameters we gave it. Anyway, I'm going to leave this up here for a second. That's the whole video. We can make this window whatever size we wanted it. I've also created a version of this that prints out a chart in Matplotlib of all of the objects' collected positions as a line graph. And right now I am working on doing that. And I did that in 3 dimensions as well, and that's going to be my next video, showing you how to do this, but it'll plot their positions in 3 dimensions. And then what I'm currently working on is doing this in 4 dimensions as a hypothetical science project into reference frames in 4 dimensions. And there will be videos on that as well. If you like this video, found it informative, thank you very much for watching. Please like and subscribe, and I'll have another video up sometime here in the next couple days. If you have any comments or suggestions, if you want to watch me code it from the very beginning all the way through, we can do that as well. Thanks again. Y'all have a nice day.